All right, let's talk about dimensionality reduction. It's one of those things in data science that can feel like a total maze. You know you need to do it, but figuring out which technique to use and when, well, that's absolutely critical. So let's dive in and make it simple.
So here's a weird question for you. Why does getting more data sometimes make our models worse? I mean, it sounds completely backward, doesn't it? We're always told more data is better. But what if adding more features, more columns in your dataset, actually just adds a bunch of noise, slows everything down, and makes your models less accurate? Well, that paradox is exactly why we're here today.
This whole problem actually has a name, the curse of dimensionality. As you pile on more and more dimensions, the space your data lives in just explodes. Your data points get spread super thin. Think of it like a handful of stars scattered across an empty universe. Suddenly, the idea of distance between 2 points starts to lose its meaning, and your models can get really confused, finding all sorts of fake patterns in that noise.
So, to really get a handle on the two main ways we can solve this, let's use a simple analogy. I want you to imagine that your complex, high-dimensional data is like a really intricate piece of folded origami. How do you represent that in a simpler, flatter, two-dimensional way? Well, you've basically got two options.
And this analogy just illustrates the difference perfectly. On one hand, you have linear methods, like the famous PCA. These are like casting a shadow of the origami on the wall. You get the main overall shape, the global structure, but you totally lose all those intricate little folds. Then you have nonlinear methods, like UMAP. These are more like carefully, and I mean carefully, unfolding the origami. The goal here is to preserve all the local relationships between points, revealing the hidden, complex structure that was tucked away inside all those folds.
So how do you choose? Do you cast the shadow or unfold the paper? Well, it all comes down to a pretty straightforward decision-making process. We're going to walk through 3 key questions that will point you to the right technique for your project every single time.
Okay, first question, and it's the most important one. What are you actually trying to do here? The best technique isn't universal. It completely depends on your objective. Are you just trying to get a feel for your data to see what's in there? Or are you getting it ready to feed into a machine learning model?
You've got to use the right tool for the job. If your goal is just visualization, you want to see clear, separated clusters, that's where nonlinear methods like UMAP and tsne are amazing. If it's all about pre-processing for a model, you probably care more about speed and reliable structure, which makes PCA a fantastic starting point, though UMAP is a really strong contender there too. And hey, if you're lucky enough to have labels and your goal is classification, then a supervised method like LDA can be perfect for finding the dimensions that really pull your classes apart.
On to question number 2, and this one hits on a really crucial trade-off. Do you need to be able to explain, in plain English, what your new simplified features actually mean, or is pure predictive power the only thing that matters?
See, this leads you to a fundamental choice. You can do feature selection, which is kind of like being a minimalist. You just keep a subset of the original features you started with. This is awesome when you need to explain your model's logic to someone. On the other hand, you have feature extraction. This is more like being an artist. It creates brand new features by mixing and mashing up the old ones. These new features, like the components in PCA, can capture really complex patterns, but they're a whole lot harder to interpret.
And finally, our third question. This one gets right to the heart of your data's actual shape, its geometry. I mean, does it basically lie on a flat plane, or is it all twisted and tangled up in some complex, curvy shape? This is really the core of that linear versus nonlinear decision.
This table right here is pretty much your go-to reference. PCA is your lightning-fast, easy-to-explain baseline. It's perfect for data that's more or less linear. UMAP, that's your modern, flexible choice. It handles nonlinearity really well, and it strikes a great balance between speed and quality for both looking at your data and prepping it for a model. And then you've got autoencoders, the deep learning approach. They're the most powerful option for really complex, nonlinear data like images or audio, but they are slow to train and they're the least interpretable of the bunch, by far.
You know, since PCA is so often going to be your starting point, let's just quickly walk through how to actually use it correctly. Think of this as your standard operating procedure before you even think about trying something fancier.
So there are really 4 essential steps. First, and please never ever skip this, you have to standardize your features. This just makes sure that features with really big numbers don't totally dominate the whole analysis. Then you compute the components. These are the new dimensions that capture the most variance in your data. Step 3 is the crucial analysis part, using something called a scree plot. And finally, you project your original data onto the handful of components you decide to keep. So the big question is, how many components do you keep? Well, the scree-plot is your absolute best friend here. What you do is you plot the amount of variance explained by each component, one by one, and you're looking for the elbow, that spot on the graph where the line starts to flatten out. That's the point of diminishing returns, where adding another component just isn't worth the extra complexity.
Now, a common rule of thumb you'll hear people throw around is to keep enough components to explain 95% of the total variance, and that's a great starting point, for sure, but just remember, it's not some magic number. If you choose too few components, you risk throwing out really valuable information, but if you choose too many, you end up keeping noise that can actually hurt your model. The sweet spot, as always, really depends on your specific goal.
Okay, now for a really important section. Let's talk about the red flags, the super common mistakes that people make all the time with dimensionality reduction. Seriously, avoiding these will save you so many headaches down the road.
Mistake number 1, and this is a huge one, using TSNE for pre-processing. Look, TSNE creates these beautiful visualizations. It works by kind of exaggerating the separation between clusters to make them clear. But the distances between those clusters, they're an illusion. They're not meaningful. So feeding those distorted relationships into a machine learning model, well, that's just a recipe for disaster. TSNE is for your eyes only.
Mistake number 2 is just forgetting to scale your data before you run PCA. Since PCA is all about distance, if you have one feature that's measured in the millions and another that goes from 0 to 1, guess which one's going to run the show? The bigger one will completely dominate your results, and they'll be pretty much meaningless. So always standardize first.
And mistake number 3 is blindly picking a number of components, like say 2, just because it's easy to plot. No, you have to have a reason for your choice. Use that elbow in the scree-plot as your guide. Or even better, test how different numbers of components actually affect the performance of your final model. Let the results justify your decision.
Okay, so let's bring all this together. We've talked about the theory, the workflow, the big pitfalls. So here's a final toolkit, a little summary, to help you choose the best tool for the job every single time.
Think of this cheat sheet as your quick decision-making guide. If you need a fast and interpretable baseline, always start with PCA. For high-quality, beautiful visualizations, UMAP is your modern workhorse. Now, if you're dealing with really high-dimensional, sparse data like text, don't forget about simple feature selection. It's often way more effective. And finally, when you know you're up against some deep, nonlinear complexity, that's when you bring out the power tools, UMAP and autoencoders.
Now, you might be thinking, this all feels a little bit like magic, but here's the cool part. It's not. It's actually grounded in a really powerful mathematical idea, a theorem, that basically guarantees that you can take high-dimensional data and squash it down into a much lower dimensional space while preserving the important distances between points. This is the theoretical bedrock that makes all these techniques actually work.
And so we end with this thought, choosing the right number of dimensions from a scree-plot, or deciding between a model that's easy to explain versus one that's a tiny bit more accurate but a total black box. These aren't just technical decisions. They require your judgment. This is where the science of data meets the art of interpretation. The tools can show you the trade-offs, but in the end, you're the one who has to decide where to draw the line.